Okay, today guys, we're going to be looking at standing waves in air columns, okay? But before we do that, what we need to do is just have a very, very brief recap of harmonics, okay? Now, first of all, we can see here, this is our fundamental or our first harmonic. And with the first harmonic, we have a fundamental frequency, F0 we can call it. And we know that the wavelength is equal to twice the length of this string. So if this was the length across here, you would need to do twice that length to get the wavelength. As we go through the harmonics, for the second harmonic, this is pretty much defined really by the fact that you need twice the fundamental frequency to create that second harmonic. The third harmonic has 3 times the fundamental frequency, the fourth 4 times the fifth times it keeps going on. This could effectively be calculated from our equation. The speed of the wave is the frequency times by the wavelength, because as we can see that the wavelength is going to be, the wavelength for the second harmonic is half of what the wavelength was for the first harmonic. The wavelength for the third harmonic is a third of what the wavelength was for the fourth harmonic. For the first harmonic, the wavelength for the fourth harmonic is a quarter of what it was for the first harmonic. And obviously, if you've got half the wavelength, you're going to need double the frequency. If you've got a third of the wavelength, you're going to need 3 times the frequency to create the same wave speed. Okay? So this is what we looked at before. These are our harmonics. Now we're going to be looking at something very, very similar with air columns, but there is a very important difference. And what I want us to notice here is that if we look at all of these, so this would be if you were creating waves on a string or something, if we look at all of these, you can see that we have a node at the end on every single one of these all the way down, okay? Air columns are going to be slightly different to this, okay? And that's the key thing. So I'm going to rub these out, and what I'm going to do is I'm going to show you now the key difference for when we start looking at waves in air columns, and I'll explain to you what we actually mean by an air column as well. Okay, so the most important thing for us to consider when we're talking about waves in air columns, and we literally mean a column of air. So if you imagined a measuring cylinder, is the best way to think of it. If you took a glass measuring cylinder, I'm not sure if that's the correct chemical diagram, but it's how I'm drawing it. If you take a glass measuring cylinder, this is literally a column and it's got air in it. You could adjust the amount of air, the height of that column, etc. if you fill it with water, but ultimately it is just a column of air. And if we were to create some sound near the top of this, you would end up with some sound waves going up in here, the longitudinal waves, etc. Okay, and you would end up with a wave in a column of air. That wave could travel down, it's going to reflect, it's going to come back up, and when the progressive wave moving down reflects and it travels back through itself, it's going to superpose, and you're going to end up with nodes and antinodes, creating a standing wave. So that's what we're talking about here. But the key thing we have to understand with air columns is that you have 2 situations. One is where you've got a closed end and an open end, and one is where you've got an open end and an open end of both here. And the most important thing here that we're looking at is we need to know this fundamental fact, and that is that you will always have a node at a closed end and an antinode at an open end. So on this one here, we're going to have an antinode and have another antinode. So if we were to create some kind of standing wave, and we're going to look at what all the harmonics are in a moment, you could have something along the lines of this. That would be one particular example of a standing wave in a tube with one closed end and one open end, because we have a node here and we have an antinode here. On this one, you could have something that's going to look more like this. And again, this is just a random harmonic that I've drawn. It's not a particular one, but you can see that we've got an antinode here and we've also got an antinode here. What we're going to do now is we're going to look through what the different possible harmonics are, okay? So before I do that, what I would do is I'd suggest to you that you could pause here and you could have a go, and you could see if you could draw maybe what you think the first 3 or 4 possible harmonics are for this situation and for this situation. What do you think the fundamental would look like? What do you think the following harmonics are going to look like? Okay, I'm going to draw them on the board here now, and you can see if you get them the same as what I do. Okay. So over here on the left hand side, what we've got is we've got some tubes which have got a closed end. On the right hand side, we've got some that are just open, okay? Now, I'm going to start over here on the right hand side as you look at it here with the tubes that are open at both ends, and we're going to draw what the possible options are here, okay? Now, first of all, we could start down here and we could finish up here. So we are going to say that we have got something that looks pretty much just like this. I'm going to draw in the other half to it, the kind of the dotted half as I draw it as well. Okay, and this is going to be our fundamental. This is our first harmonic. This is the most simple way that I can get from an antinode here and an antinode here. Okay, if we look at the next one, it's going to go from here, it's going to go up to here, and it's going to come back down again. You don't have to start at the bottom, you could start at the top. So I'm going to go up here, okay, and something like that. This one is going to start down here. It's going to go up, down, and back up again. This one over here is obviously slightly different. Over here, we've got the closed at one end and we've got open at the other. So we're going to have obviously a node at this end. So these are all going to start in the middle here. Okay, we've got a node at the left-hand side and an antinode up here. Now again, I could either go from the middle to the top or from the middle to the bottom. It doesn't really matter. I'm going to go middle to the top. So this one here is kind of going to look something. I mean, it's very straightforward. Looks something a little bit like this. And if I draw in the bottom up here, it's going to do something like that. Now the next one, I'm going to start in the middle. I'm going to go up to the top and then down to the bottom. So it's going to go up to the top up here somewhere and down to the bottom here, down here, up here. And we're going to keep going. So this one's going to have to go up to the top, down to the bottom, and up to the top again. Okay, so we're going to label these up now. We're going to decide what harmonic it is. Now, over here, we've got our first harmonic. This is because this is going to be the fundamental frequency. So this is the first harmonic, okay? And again, this one over here, this is our fundamental frequency. So this is going to be the first harmonic. Now, if we look at the next one, I'm going to look at this one here. You can see that in this situation, the wavelength is half of what the wavelength was for this one, okay? Because in the first one, we can clearly see that in this situation here, I've got too many colours going on, try green. In this situation here, okay, if this is L, we can say that the wavelength here is 2L, because a full wavelength would have to come over to here. Okay, in this situation here, I can say that the wavelength is equal to L, so we've got half the wavelength. Now, half the wavelength for the same speed of wave means that you're going to have double the frequency. So we can say that this here is going to be 2 lots of F0, so it's the second harmonic. Okay, and it's going to follow the same pattern as we go down here. We can see, if we look at this one here, that that would be 1 wavelength there, okay, and we've actually got 1.5 wavelengths in here. So it basically is exactly the same as the normal harmonics that we saw before, except that instead of having a node at each end, we've got an antinode at each end. So here, what we're going to say is we're going to say that the wavelength is actually here 2/3 of the length. This one's going to be 2/4, i.e. half of the length. So we're going to say that this is obviously then the third harmonic with a frequency of 3 lots of F0, the fourth harmonic, and the fifth harmonic. Okay. Now, that's fairly straightforward, okay? I'm going to clear this up here, just so that we can now look at this second one over here. Now, this is a little bit trickier, because clearly we can see here that this is not just like a case of doubling or halving or anything like that, okay? What we've actually got here is we've got a quarter of a wavelength in here. So we can say that we've got, if this is L, we can say that the wavelength is in actual fact 4 lots of L, okay? Because you would have to go this up to the top, and if we doubled it, you get back down here, and then you've got the bottom half over here as well. So you've actually only got a quarter of a wavelength going on in here. And in this situation here, we still haven't achieved a full wavelength. We still haven't got a full wavelength. We've only got 3/4 of a wavelength here. And what we're going to say here is we're going to say that here, so we can obviously we can say that L is equal to 3/4 of a wavelength. So we're going to say that a wavelength is equal to 4/3 L. Okay. Now, and if we go down here, that is a full wavelength. So we've actually got a wavelength and a quarter of a wavelength. So here we're going to say that L is equal to a wavelength and a quarter of a wavelength. So here we're going to say lambda is equal to 4/5 L. That is 5. What we can actually see is that the wavelength in this situation is actually a third of the fundamental wavelength, effectively, okay? So we had a wavelength here of 4L, this one is 4L over 3. So the wavelength here is actually a third of what the wavelength here is. The wavelength here is a fifth of what the wavelength here is. And by matching that up with our equation V equals F lambda, we have to know, assuming again that V is the same, which we're talking about air here, we're talking about the speed of sound in air, so assuming the air pressure, density, things like that haven't changed, we can assume the speed of sound is fairly constant. So if the wavelength here is a third of what the wavelength here is, we have to say that the frequency needed to create this wave in this closed end air column, the frequency here is going to be equal to 3 times by the frequency here. And that means that what we actually say is we say that this is known as the third harmonic. Even though it's the second possible way of creating a wave in this column, there is no such thing as a second harmonic in this this situation where we have a closed end and an open end. The next one is going to be known as it's 5 lots of the fundamental frequency, and this is the 5th harmonic. So what we have down on this side, this would obviously then be the 7th harmonic, and this would be the 9th harmonic. Okay, where down here I can say with the 9th harmonic, I can say that lambda is equal to lambda is equal to 4L over 9 is the best way of saying it. This would be 4L over 7, essentially. Now, it's really important that we see this difference, okay? So with a closed end, we've got a node, and an open end, we've got an antinode, and therefore, because of what I've shown you here, you cannot actually create a 2nd, 4th, 6th, and 8th harmonic, etc. So really important differences here, okay? Okay, so looking at this, there's a couple of questions you might need to kind of ask yourself. So first of all, well, just on a side note, it's useful to think what are the examples of these, okay? If you look at this one here, an example of this with a closed end would be something like a milk bottle example or something like that. You've all probably blown air over the top of a milk bottle and made a sound. If not, well, I don't know, try it. But the physics behind a milk bottle is going to be slightly different to this because the shape is obviously not just a perfect cylinder. It's to do with, the equations involved factor in the volume of the air inside and the area of the opening at the top, things like that. This is obviously a simplified version, but the actual wave that's going to be created inside that milk bottle is going to be very similar in a sense to this. But anyway, this one over here is going to be something more like a panpipe or a flute, where you're going to have like an open end at the top and at the bottom. Okay. There is a big advantage. There is one big advantage to these over here. Okay, to these ones here when making musical instruments, and that is that if you were to imagine making like a church organ or something. Okay, now church organs. Okay, you could imagine a pipe. Now, I'm not an expert on musical instruments, and I don't know the ins and outs exactly how church organs are made. But if you were to make an organ pipe, for example, and you wanted to make a really low sound, you wanted to make a very, very low sound with, you know, I don't know, 20, 30, 40, 50 hertz, something like quite a low note. What you're going to find is that you would need to make a very long pipe. Because if the speed of sound is, it's about 340 meters per second, but let's just go for some very, very simple, got text. Let's go for some very simple calculations here. I'm just going to say, let's say the speed of sound was 300 meters per second. And we said that we wanted to make a frequency of 30 hertz, for example. Our wavelength is obviously going to have to be 10 meters. Now, if our wavelength, let's just shut the phone up here. Silence. Now, if our wavelength is 10 meters, okay, now if we look at a pipe that is open at both ends, we know that our pipe is going to have to be at least 5 meters long, because in this situation here, okay, the wavelength here to create the fundamental, if your wavelength is 10 meters, your pipe is going to have to be 5 meters long. Now, 5 meters might not sound like a lot, but it's quite a large pipe. Okay, 5 meters is a big instrument here. In this situation here, we know that the wavelength is actually 4 times the length. So with a closed end, that you could create the same sound, or the same pitch sound. Anyway, I don't know about quality, but you could create the same pitch sound with a pipe that is half the length of what the open end would be. Because with a wavelength of 10 meters, you could create this with a pipe that was only 2.5 meters long. So, you know, there are advantages, and there's probably advantages to these as well. But like I said, I'm not a musician or an expert in that front anyway. Okay, what's really important also is that we're going to look at the difference between each harmonic as we go down. And we can see here that the first possibility here, so the first harmonic here, we're going to say that L is equal to half a wavelength. Okay, and in this situation we're going to say L is equal to a full wavelength, and in this situation we're going to say L is equal to 3.5 wavelengths, also 3/2 wavelengths. And the key thing here is that every time we increase, it gets longer effectively by half a wavelength. Okay, and that's something that's very important to look at, to notice, because we're going to talk about this as we go a little bit later on for the next activity. And the very important thing is that the same happens over here. Okay, so in this situation, we're going to say that L is going to be, I'm going to write it down here to make it clearer. So in our first harmonic, okay, we're going to say L is equal to lambda over 4. Now in our third harmonic, which is actually the next one, it's the next available possibility, okay, we're going to say L is equal to 3/4 lambda, which is an extra half of a wavelength. And in the next possibility, we're going to say L is equal to 5/4 lambda, which again is an extra half of a wavelength. And again, that's really important, and we're going to talk about that in the next thing that I'm going to do, and I'm going to clear this board before I create that. Okay? Okay, now I'm going to talk you through an experiment. This is actually one of the possible PAGs which we could do in a lab, but I can't do here, but I'm going to talk you through it anyway, okay? What we're going to do is we're going to measure the speed of sound using a column of air and the sound that goes on. So I'm going to give you a little bit of background. So basically the setup for this experiment is you're going to take a tube which would be a glass cylinder, like a measuring cylinder, but without the bottom on it. So you've kind of got a top or a bottom. I mean, you could just use a measuring cylinder with a close at the bottom, but what you generally do is you would then place this in water, and you can lower or raise this tube in the water to basically change the length of the air column that you're going to do. And yes, absolutely, you could use one with a closed bottom here, just like a regular measuring cylinder, and you could just fill more water in it. Either way, it doesn't really matter. But what we're going to do is we're going to be changing this length here, or this height here. That's really important. What we're also going to do is we're going to basically play some sound at a constant frequency near the top of this wave. Now, there's a couple of ways you can do that. Traditionally, what you would generally do here is you would use a tuning fork, which you've probably seen. They kind of look a little bit like this. Some great artwork. They kind of look a little bit like this, and you will tap it on something and it will make a sound, like a note. It can be quite annoying, but it will make a note at a very specific frequency, and it will last for a while. They're not particularly loud often, certainly the ones that I have available at school are not particularly loud, but what happens is when you move this tuning fork, whilst it's vibrating, you move it near to the top of here, what happens is that sound wave ends up coming in here, and it either will or it won't create a nice standing wave with a harmonic in here. And it obviously depends on whether this length is a correct length to create a standing wave at the frequency which this is vibrating. The other option is that instead of using one of these, you could just use some kind of speaker, which again, you just take an electronic speaker, play a very specific note, probably got it hooked up to a signal generator and oscilloscope, you know what the frequency is. You play a very specific note, a constant note here. Now, the key thing is that when the length of this matches up with one of the harmonics that is available from this frequency, you will physically hear the note become much louder. Okay, you get like a big raise. It's like a spike in the volume of the sound. And what you can do is you can kind of adjust the length of this. Whilst holding your vibrating tuning fork or your speaker here, you can adjust the length of the tube until you get that peak in volume, and then you know that you've got one of your possible harmonics in here. This is a closed end, this is an open end. So what you basically have there is you would have a situation where you have got quite possibly a fundamental, okay? Or it could be that you've got your third harmonic, or it could be that you've got your fifth harmonic, okay? You wouldn't necessarily know which one, you would just know that you do have some kind of harmonic there because you've got this peak in the volume, okay? Now, what we can do then is we can actually use this to measure the speed of sound. There's a few things that we can do, and I'm going to talk you through the ways we can improve the experiment as well, okay? So, first of all, we're going to talk about how we can actually identify whether you're at that peak or not, okay? So what you can do is you could have your tuning fork here, and you could have some kind of microphone set up to an oscilloscope or a computer system which will tell you the volume. And if you adjust this length, take a measurement every centimetre or every half centimetre or every 2 centimetres, whatever, you can probably choose a sensible scale. But what you will probably find is you will find that if you then plotted a graph of the volume, and this is the volume of the sound, okay, against the, if it was on an oscilloscope, it might be the signal in voltage, in volts or something like that, against the length of the tube, what you would probably find is that it would be kind of fairly low, and then it would spike, and then it would be fairly low again, and then it would spike, and then it would be fairly low, and then it would spike. And at each of these, you would be able to identify the length at which you had a harmonic, okay? So if you were to just say, oh, I think it's around about here, you wouldn't necessarily know. You'd probably be pretty good at getting somewhere in that range, but you would be, if you were doing it by just listening to it, you would have a bit of a range of length. You wouldn't know exactly where the peak was, but if you plotted a graph, you would be able to identify exactly where that peak was. So what we could do is we could do that. Now, the other issue then is how do I know whether I've got a fundamental, whether I've got a third harmonic, a fifth harmonic, a seventh harmonic, okay? Because if I just pick one, if I just wait until it's loud, all I know is I've got a harmonic. I don't know whether I've got a fundamental or whatever, okay? Now, one way you could solve this problem, and it's not necessarily the best way, but one way you could solve this problem is you could start with the tube very, very, very small, okay? So what you could do is you could start, let's just redraw this so it's a little bit easier for us to do. So if I say, I'm going to draw a big tall thing here. So you could start with the tube, for example, like this, where you've got a very, very small value of H, or L. I should call it L really, I don't know what they call it in the PAG thing I've got in front of me. But you've got a very small value of L here, and so long as you're confident that this is much less than the possible options for a fundamental, then you know that if you slowly start to increase this length, okay, then you know the point at which you get your first possible harmonic is going to be your fundamental harmonic, okay? Now, using that, you know that you then have a fundamental in here. We could just do from a single calculation now, we could actually work out what the speed of sound was. This will have a known frequency. So we can then say that our wavelength is going to be 4 times by this length, and then we're going to say that the speed of sound in air is going to be 4L, that's your wavelength, times by the frequency of your tuning fork or of your speaker or whatever it is, okay? So you could work out an individual value for the speed of sound. Now, we know by now, because we're doing A-level physics and we're some way through A-level physics by this point, we know that no physicist, no good scientist really ever wants to make a measurement or make a confident statement based on one individual measurement, okay? If it's possible, we want to change something, have some kind of independent variable, we want to change something, and we want to create a graph of results, and we want to do a calculation from a gradient most likely on that graph, okay? Now in this situation, what we would do is we would use a number of different frequencies, okay? And what we would then do is we would then be able to plot a graph, okay? And if you plotted a graph of the frequency, and you plotted a graph against 1 over the length here, okay, and I'll explain why this in a second, you're going to get a straight line here, or we should do, and the gradient, we're going to look at what this means in a second, okay? So let's look at this. If we look at, let's see why this is. Now, based on, I don't know why I just rubbed that out, I'm going to pretty much redraw it, okay? So we're looking for the speed of a wave to be the gradient. So we're going to say that we know that speed equals frequency times by wavelength. I want the speed to be the gradient, or something along the speed, maybe speed over 4 or times 4 or something like that, okay? So we're going to say this is x, so I'm going to bring this over here, so I'm going to say 1 over lambda, let's just do it step by step, times by v equals f. I'm going to bring this over here, so I'm going to say 1 over the wavelength equals, and then I'm going to say that this is going to come over here, so it's 1 over v times by f. So we can see that if I have 1 over the wavelength over here, okay, then you're going to have the frequency, and this would be 1 over, this gradient would be 1 over v. But what I've got here is I'm plotting 1 over length, and we know if we were to substitute in here, so we know that lambda is actually equal to 4L. Okay, so this is equal to 4L. So we can finally say that 1 over L, and I'm going to bring the 4 up, equals 4 over V times by F. So if you plotted this graph and you had different frequencies on your x-axis and 1 over L on your y-axis, okay, this is all assuming that we knew we could find the fundamental and we knew that it wasn't like a third or fifth harmonic, okay. So if you've got frequency here and 1 over L on here, we know that our gradient of this line is going to be 4 over V. So we can calculate the speed of sound based on this, okay. Now, this is actually what the PAG suggests from the exam board, okay. I actually am not a big fan of this. There's actually an improvement to this, and there's two reasons why the improvement I'm going to suggest is something that I prefer, okay. One reason is that what I'm about to suggest is it removes the doubt as to whether or not you've got the fundamental, okay? So we don't have to worry about this. Is it the fundamental? Is it the third? Is it the fifth? Is it the seventh? We don't have to worry about that, okay? The second reason is because it factors in a real life issue with these standing waves in air columns, okay? And the real life issue that we have is that when we create a standing wave in an air column, what actually happens is that the antinode in the real world, the antinode does not actually match up perfectly with the top of the column. It actually kind of appears just outside of the column, I think, and you have therefore some uncertainty in exactly what this length is. Okay, but we can kind of remove this issue by doing the method that I'm about to show you. Okay. Okay, so the key difference with the method is very, very similar, but the key difference with the method I'm going to show you is I'm going to say that rather than just starting from the bottom or just waiting till we find one point when it's particularly loud, and for example, just waiting, taking measurements and finding a peak and hoping that was the fundamental, what we're going to do is we're going to take measurements, we're going to find a peak, and then we're going to continue to change the length of this tube. So we're going to move the tube until we find a peak, and then we're going to continue to move the tube until we find the next peak in volume. Okay. Now the reason for that, and we're then going to look at what is this change in length. So if this is L, I'm going to call this the change in length. Okay. So the change in length from when you see one peak to when you see the next peak. Now the reason for that is because it doesn't actually matter whether I had the fundamental for the first time or not, okay? I could have the fundamental, and then I have the third harmonic, which we know that for the fundamental, if we draw these, okay? For the fundamental, we've got L is equal to a quarter of a wavelength, and for the third harmonic, we've got L is equal to 3/4 of a wavelength. We know that the difference between these, okay, is half a wavelength. And it doesn't matter whether I had the first and third, the fundamental and third, or whether I had the third and the fifth and the seventh and the ninth, or the 101st and 103rd, okay? It doesn't really matter, because what I do know is that the difference between two harmonics here is always going to be equal to half a wavelength. So if I went, it might be that I had in here the third harmonic, and then when I changed the length, I had the fifth harmonic, okay? But the key thing here is that the difference, okay, the difference is equal to half of a wavelength, okay? And we absolutely know that. It also means that we don't have to worry about this bit at the top, because I'm adding that half wavelength within the tube effectively, okay? So what I'm effectively doing is I'm adding an extra bit down here, okay? So this stuff that's going on at the top, whether the wave is actually, whether the antinode is actually slightly outside of the tube or not, I don't really care, okay? It doesn't really matter, okay? So we know that this extra bit of length is equal to half a wavelength. What this then does to our graph is it means that instead of plotting, so when we're plotting our graph, we're still going to plot our graph of the frequency. So we're using lots of different tuning forks or lots of different frequencies, and we're gonna plot this against 1 over the change in length this time, rather than 1 over the length. And this means that when we plot our graph here, we can again look at the gradient, and let's just look at the calculation. So again, I'll just work through. So V equals F lambda. So we know that lambda this time, okay, is equal to 2 lots of the change in length, okay? Because remember, our change in length is equal to half of a wavelength. So when I rearrange this equation, I'm going to say 1 over, I'm going to bring the 1 over the change in length. So let's just bring the 2. 1 over 2 times the change in length is equal to, bring the V over here, 1 over V times by F. So when I'll put the 2 back up here. So finally, I'm going to say 1 over the change in length is equal to 2 over V times by the frequency. So this time, my gradient of this would equal to 2 over V. Now, so long as you can describe how you get this, and if you can understand where these graphs come from, it doesn't really matter which method you use. Like I say, the exam board have suggested the one where we're just looking at the fundamental, and it's absolutely fine. Chances are you probably will find the fundamental. Usually, these, the disadvantage of my method is that you would need a longer tube available. Okay, so it might be that you're limited by the size of the tube, and you can probably only get the fundamental in there, which means that you're probably going to have to go for that first method. But if you've got a long tube where you can adjust the length enough to get multiple peaks in volume, then this method is going to be, in terms of the physics, this method is going to be a superior method. Okay.